Hey, welcome back to Fat Mama Physics. In this video, we're going to do more examples of the Feynman diagram. We are now on example 3. In this video, I am going to do example 3 and example 5. So I am sorry, a little bit out of order, but just to gauge the length of the videos, that's what I will do. In the decay, it looks like a sigma here. Sigma minus gives off a neutron and a negative pion. Okay, it takes weak place through a weak interaction. We need to figure out why it is weak and also draw the Feynman diagram for this decay. Usually for the most cases, actually for all the cases, you should not need to memorize any of the unique particles. It will tell you the core composition of those. But you need to be able to take the core composition and talk about the charges that are involved and hopefully break them down. So here we go. We are told what the sigma minus is and the pion negative is as well. This n here is just a neutron. So we're going to try to draw the Feynman diagram for this decay. Before we draw anything, I would recommend taking all of these particles and writing their constituents or the core composition to figure out what is happening. So I have a sigma minus. That's a DDS, a down, down, and a strange. Strange. And a neutron, we know it's a up, down, down. And last but not least, a pion minus, it's going to be an anti-up and a down. So it looks like what is happening here is we have a baryon turning into another baryon. So it looks like to minimize the amount of changes, the D's are common, the down quarks are the common factor, and the strange quark and the up quark are the two ones that are different. So it looks like the strange quark is getting converted into an up quark. And this, it's here we have a pion, and it has an anti-quark and a quark pair. So it is a meson, and usually an anti-particle and a particle pair can be produced through a pair production of some sort, usually through an exchange particle. So it looks like what is happening is this quark is decaying into this quark, which then releases a boson, which then produces this pair over here, which is the meson. So let's draw the Feynman diagram for this one. And we're going to need enough space. So we can't take up too much space, since I need enough space to make an exchange particle go down to become the meson, which is the particle-antiparticle pair. So starting with ds, and s is being the one that is different, I'm going to put that on the bottom. The top is ddu, which is the product. We know that this guy over here is a sigma, and this guy over here is a neutron. These two, the down quarks are going to be the same. The strange quark gets converted to an up quark, and something leaves. A mediating particle is produced. Okay, we don't know what that is, but we know it produces the pair involved, which includes the anti-up and the down quark. And since the up is anti, we're going to draw the arrow moving backwards in time and the down quark moving forwards in time. Okay, so this is the basic Feynman diagram. We're not done yet because we need to figure out what is mediating this interaction. So we know it's a weak interaction by what it's telling us, but it's also weak because we know that the strangeness is not conserved. Notice that there's a quark in the reactants, but no strange quarks in the products. So whenever you see a strange quark, that always gives you a -1 number for strangeness, and the only kind of interaction that has that factor where strangeness is not conserved is your weak interaction. So because of that, we know that the W plus, W minus, and the Z0 boson would be possible in mediating this interaction. And knowing that, let's figure out the charges involved to figure out whether it's W plus, minus, or Z0. An anti-up quark has a charge of, usually it would, for the particle up quark, it's 2/3. But since this is the antiparticle, it will have the opposite charge, so negative 2/3. The down quark has a negative 1/3 charge. So since these two charges added together is going to give us a net -1 charge, the charge coming in has to be negative, meaning that it has to be mediated by the negative W minus boson. We can doubly check that with the previous junction by going here. We know that let's see, we have a strange quark. Strange quark has a negative 1/3. So a negative 1/3 to this junction, it loses a whole negative charge, and that's going to become a positive 2/3 charge. So charge conservation checks out for both of these junctions. So here is the complete Feynman diagram. And why is it the weak interaction? Because strangeness is not conserved. So my poorly worded two phrases here is that here the strangeness is not conserved, and it's only in the weak interactions in which the strangeness is not conserved. Okay, so that's the idea. All right, so I did say we're going to do example 5 before we go on and do the long example 4, long example 6, and 7 questions. So with the idea of scattering, the photon may get, say, absorbed by the positron, and then later in time it gets re-emitted out again as a photon, so that there is some interaction between the two. And so what we could do is, first of all, if we probably want to show the fact they do meet. So a positron coming in like this, meaning that it's an antiparticle, so the arrows have to point backwards in time, if that's the case. And then we have a photon coming in, so they meet up here. In which case, if a photon probably will get momentarily absorbed by this positron, after it absorbs a photon, the photon leaves since it does scatter. So here we have another vertex. At some later point in time, this photon gets scattered back out again, and then the positron leaves going forward in time. And since it's an antiparticle, the arrows are drawn backwards. So it doesn't matter if you put the photon up here or if you put the positron down here. It does show that they are in fact leaving away from this vertex. So this would also work as well. Okay, so there you go. There is a scattering of a photon off of a positron. Okay, so that's the that's the end of this video. Next video, I'm going to do a full example 4 and a full example 6, and then 7 will be the last one. Okay, so I thank you for watching. I wish you good luck. Fat Mama Physics signing out.